So having made a video on the fast carbon cycle, I thought I'd make a video on the slow carbon cycle. And the slow carbon cycle relies on the slow release of carbon, usually through rocks, okay? And one of the best ways to illustrate this is using those. This is the shell of a snail, okay? My 2-year-old daughter is obsessed with snails at the minute, probably because they don't move very fast, and so she can follow them around the garden. Unfortunately, when snails die, their body, you can see there, isn't there anymore. It's been decomposed, and arguably that carbon's been released into the ground through the fast carbon cycle. The shell, on the other hand, takes a lot longer to decompose, and the shell illustrates a lot of what happens in our oceans. So you might have heard the claim that the oceans absorb carbon. They don't physically just suck the carbon into the water. Okay, a lot of the carbon that oceans absorbed is through these shells. Okay, whether that's a bone carcass. So you might remember watching a video of a decomposing whale carcass. Well, when that whale dies, it goes to the sea floor. Okay, the meat, the bones, all they get decomposed and stay on the seabed. There's also millions and millions and millions of what we call in French crustacea, which are these shell-based animals. All these shells are made out of carbon. When they die, these shells fall to the bottom of the ocean, and then they pile on top of each other. And then they get compressed and they create what we call sedimentary rock at the bottom of the ocean. Okay, another one which that happens in the ocean is these phytoplanktons, which are algae in the water. They absorb carbon through photosynthesis, and when these planktons die, they fall to the seafloor. Okay, so actually at the bottom of the seafloor, you've got an unbelievable amount of carbon that just gets deposited. What happens eventually is that carbon gets layered and layered and layered and layered and layered, and with the movement of tectonic plates, that carbon can move. Okay, can also get compressed and heated and create a metamorphic rock, for example, if it gets pressurized and heated up to really high temperatures. But ultimately, what will happen at a convergent plate margin, which at key stage 3 and key stage 4, you'll know as a destructive plate margin, is that you've got two plate margins that meet up. You've got one, let's say this is oceanic, and this is going to be the continental. The oceanic one is denser, it's heavier, so it's going to sink underneath the continental one. Okay, as it sinks, the oceanic plate sinks below. That plate contains all the carbon that's been deposited at the bottom of the ocean. Okay, so as it sinks into the mantle, that plate will start to melt. Okay, in the subduction zone, the plate will melt a bit like a biscuit in your cup of tea, and all the carbon that's contained into that plate will gasify. Okay, because it heats up, a lot of carbon will turn into carbon dioxide and it'll create more magma and molten rock because it's melting, but also release some carbon and some gases underneath. As a result of this, the pressure builds, and usually at a convergent plate margin, when ocean meets continent, around there where my knuckles are, you end up having volcanic chain. Okay, and the best example of this would be in Italy. We've got the Stromboli, the Vesuvius, Mount Etna. All this gas gets released through volcanoes. When those volcanoes erupt, they release that CO2 back into the atmosphere. They'll also release rocks that will contain some carbon. These are called igneous rocks. And ignition, like a fire, will be released into the atmosphere. Okay, that process takes millions and millions and millions of years because plates don't move quickly. Okay, a number I often use at key stage 3 is that the plates around Iceland that are in this case divergent or constructive, they move away from each other. They move away at the speed of about 4 centimeters a year. Okay, so we're not talking incredibly high speed, which is why the slow carbon cycle is called slow. The speed at which all this happens from the let's say sea snail that dies, falls to the sort of floor of the ocean, creates sedimentary rock, for that rock to then move into position to then subduct on a continental crust, release its gas as CO2 through a volcano. That will take millions of years. Okay, an alternative to that is if it doesn't get released by a volcano, it fossilizes. Okay, and you might remember too that fossilized animals, shells, any living creature that fossilizes, if in the right conditions, will create a fossil fuel. And that fossil fuel from fossilized animals is oil and gas. So oil and gas we use in our everyday life, like in the cars and in the heating of our homes, realistically are fossilized animals from millions of years ago, we're burning the carbon remains of those to create our energy. Okay, if plants, like you've got loads of plants in my garden behind me, if those get fossilized in swampy conditions over millions of years, they'll turn into coal, another fossil fuel. Okay, so the kind of other way in which you can release the carbon from a slow carbon cycle is all these fossilized remains then burnt and the CO2 gets released. And what humans have basically been doing is that carbon cycle has always happened. Okay, volcanoes have always erupted, the ash will then fall, animals have always died, plates have always moved. Okay, so that cycle's always happened on its own. Fossilization has always happened too. Okay, and sometimes you get carbon that gets released because there might be a fire that'll happen in an area that has high gas content and then release some CO2 there. However, what humans have done is we've accelerated that cycle. So by defossilizing or by extraction of fossil fuels, we've released the carbon from the slow carbon cycle faster than the carbon cycle can absorb the CO2 again. Okay, so we've basically transferring carbon from slow carbon cycle to the fast carbon cycle, in essence, at a faster pace than our planet can absorb the speed at which and absorb that CO2. And that is the sole reason why the amount of CO2 in the atmosphere has increased. It's because our planet is still absorbing it. Okay, arguably, the more CO2 you have in the atmosphere, the more plants can photosynthesize, the more CO2 they can absorb. But we're releasing that carbon much, much faster than plants and the planet can absorb it. Therefore, the content of CO2 in the atmosphere increases, affecting our temperatures, etc. Okay, and that is how humans have destabilized what used to be a perfectly dynamic but perfectly balanced equilibrium. I hope that all makes sense, and obviously that's something you're going to be doing loads in class anyway, so don't worry if you don't. I just thought I'd kind of, through video content, provide you with a bit more of an illustration of how the carbon cycle works.